A slope field, or a directional field, is a graph which has at the points t comma y a line segment with slope given by the equation for y prime. And based off of all of those line segments, we'll be able to get a good idea of what the solutions to the differential equation look like. We have the differential equation from our previous problem to be y prime equals 10 minus 0.25y. And we could start developing the slope field graph for this differential equation in this two-dimensional grid here. On the horizontal grid, horizontal scaling, we'll have t's. On the vertical scaling, we'll have y's. Let's say I populate this with 1, 2, 3, 4. And I'm selecting, conveniently, the values of 35, 40, and 45. So when I look at the sort of combinations of t's and y's, I can have my 1 comma 35, 2 comma 35, 3 comma 35, 4 35, and all the other points above here to create this array of points. For each one of these points, I'm going to go ahead and compute the derivative at those points. For example, let's say I'm focusing my attention on this point right here. So at the point where my t is equal to 1 and my y value is 35, let me go ahead and compute the derivative. So the derivative is going to be 10 minus 0.25 times y. So that gives me 10 minus 0.25 times 35. Let me go ahead and compute that out. I get 1.25. So for that first point, I'm going to have a positive slope of 1.25. It's approximately that right there. Notice that if I were to do the same analysis for these 3 points, I would be plugging in the corresponding t's and y's into this formula, but there is no t here and the y values are all the same. So the slopes for those 3 points is going to be exactly the same. So I can simply copy the same line segment for those other 3 points. Continuing my analysis for this point of 1 comma 40. I can compute y prime to get the slope of my line segment. So that's 10 minus 0.25 times 40. And that's going to be 0. So for this point, I have a horizontal line. And in the same way, I would have a horizontal line for these other 3. And finally, at 145 rather, computing the derivative y prime at that point to 10 minus 0.25 times 45. I get negative 1.25. So at that point I get a negative slope. So at these those 4 points, we have those 4 line segments with a slope of negative 1.25. So ideally, we would do this a whole bunch of times and populate this whole plane with a whole bunch of line segments. And from those line segments, I can start getting some insight of what the graphs will look like, what the solutions will look like. That could potentially take a long time, and this problem is particularly easy because it has nice numbers. But we're going to have this cool tool that's going to allow us to do this problem or develop this slope field using some graphical utility, GeoGebra in particular. So on Google, you can type in slope field generator. So when you type in slope field generator, you get a whole bunch of options. I particularly like this one with GeoGebra. Press that. And it asks you, what's your differential equation? Y prime equals what, right? Notice that here it wants your function to be a function of x, not of t, so be aware of that. So our function, our differential equation is 10 minus 0.25 y. And if I had a t here, I would need to replace that t with x's, right? So be careful when you input that information in there. Let me press enter and see what I get. Okay, so sometimes you have to manipulate the window to get something accommodating. In particular, I think our y values are too low. Let me kick this up to maybe 60 and see if I get something interesting. Aha, there we go. So here's the line segments for a y value of 35, the line segments for a y value of 40, the line segments for a y value of 45, right? And if we had some known values for our graph, let me actually copy that. If we had some known values for the graph, let's say we had some insight about the initial amount of morphine that the person had. So maybe this person is being moved from one part of the hospital to another part of the hospital and they already gave him some morphine. So let's say this person already came in with 5 grams already in his body. Then this corresponds to the point 0, 5, right? And 0, 5 would be this point right here. Your t is 0, your y value is 5. And then I can use these this slope field to get a sense of where the graph is going to be moving as I head towards the right-hand side. So notice that around the neighborhood of this point, all of these line segments have a positive slope. And I can use these line segments to sort of carry me through and consider what the rest of the graph will look like. So consider what's going on here. Every hour, this person is getting 10 milligrams of medicine. Let's say this person is receiving this dosage for a whole week. I know that's really impractical, but let's just say hypothetically speaking, this person is receiving that same dosage, 10 milligrams per hour, every hour for a whole week. You might think that the amount of morphine is going to be gigantic, right? He's going to have like over like 300 milligrams of morphine in his body. But that's not what this graph is telling us. This graph is telling us that the amount of morphine in the person's body is going to be leveling out. And the value that it's leveling out to seems to be about 40 milligrams. So this dynamic of the morphine being introduced into the person's body and the body metabolizing it and excreting it is sort of balancing itself out. And ultimately, that person will have a horizontal asymptote of 40. So in other words, his body will level out to always have about 40 milligrams of morphine. On the flip side, Let's say that instead of 5 milligrams of morphine, we started out with 55 milligrams of morphine. So this corresponds to the point 0, 55. This point on the graph corresponds to this point right here. And again, I can use the slope field to get a sense of what the rest of the graph will look like. And the rest of the graph will look something like that. So again, this person might have come from another part of the hospital where they maybe gave him more morphine because maybe they just did surgery and they needed a higher dose. Then when he's in our room, we give him 10 milligrams per hour, 10 milligrams per hour, 10 milligrams per hour. And again, consider what happens on the long run. The amount of morphine in his body isn't increasing, it actually goes down. And it starts leveling out to that same 40 milligrams per, 40 milligrams total. So whether you start down here, it's going to go to 40, or you start up there, it's going to go down to 40. If we were to go back to the SlopeField generator here, there's a little tab here that allows you to visualize what a solution looks like given an initial condition. So this point A, I can move all over this grid. If I move it over to the point 0, 5, that's close enough. This blue graph represents the solution to our differential equation. If I move it up to the point 0, 55, that blue graph represents the solution to the differential equation with that given point. So these SlopeFields can be really valuable to get a qualitative idea of what the solutions look like without necessarily having to solve the differential equation.